Our next presentation is from Brad Henderson from Los Alamos National Lab. The title of his talk is Thermal Gradients in the Near Surface of Lunar Regolith.
So, good morning out west, good afternoon out east. This is some work I did with Bruce Jakosky a while back. Wanted to present it to this workshop. Next slide, please. So as an introduction, particulate materials in airless environments have very low thermal conductivity as a result of their granular nature and the lack of interstitial gases. And when the surface temperature gets high, like on the day side of the moon, the heat transfer is dominated by radiative processes as opposed to conduction. And cooling to space creates significant thermal gradients in the top few hundred micrometers of the surface. And to study this problem, we modeled the radiative and conductive heat transfer in the top few millimeters of a particulate medium to look at the magnitude of these near-surface thermal gradients. The original application was to understand the effects of thermal gradients for thermal infrared emission spectroscopy, but their presence might be relevant to upcoming activities planned for the lunar surface, and that's why we're presenting here today. Next slide, please. So this slide is to look at different heat transfer regimes, both conduction dominated and radiation dominated. So if you have solid rock or particulates on a planet with significant atmosphere like Earth, conduction dominates those regimes. That figure in top middle is supposed to represent a particulate on Earth. And for typical values of thermal conductivity, a linear thermal gradient over 500 micrometers is small. And an example of that computation is at the upper right. So in addition to the gradient being small, it actually flattens out near the surface as a result of energy conservation wherever the thermal emission is starting to escape to space. As opposed to that, in a radiation-dominated environment, in considering, for example, on the moon, where you have these fluffy particulate media with no atmosphere, in the past, these have sometimes been referred to as fairy castle structures. Conduction is limited to grain contacts. And in this environment, radiation dominates. The temperature gradient adjusts to maintain a constant flux. You get significant cooling to space, and as a result, large thermal gradients form, and that's what I'm showing at lower right. Both of these examples, top and bottom, were computed for heating from below, but we're about to do solar heating in the next slide. So next slide, please. So again, to model this problem, or to look at this problem, we used a model, a one-dimensional layered thermal model, top few millimeters of a particulate medium, and that model includes both conduction and radiation. Thermal conductivities are appropriate for the lunar surface with no interstitial gases. For radiation, we used formal radiative transfer theory, scattering computed, or the scattering parameters computed using Me theory, assuming anisotropic scatterers. We did this for two different materials, the mineral quartz and the rock basalt. We varied the particle size, and the samples were heated from above by sunlight using a solar constant appropriate for the lunar surface. The time-stepping model, which means that we let it run until the temperature reaches steady state. The original application was, after it reaches steady state, to compute the thermal infrared emission spectrum. So I'll show those results as well. Next slide. This slide compares solar heating versus infrared cooling. The vertical axis is a parameter called the thermalization length. This represents the length scale over which visible radiation and infrared radiation are absorbed. It's a function of particle size, that's the x-axis. The pluses are for visible, and the stars are for the infrared. And what you can see is that in general, the length scales over which radiation is absorbed are longer in the visible than they are in the infrared. So what that means is the thickness over which radiation is absorbed is thicker in the visible than it is in the infrared. And what this means is that infrared cooling happens over a thinner layer than visible absorption, and that affects both the location and size of the thermal gradient. You can see that the disparity between visible and infrared is greater on the left for quartz particulates than it is on the right for basalt particulates. Next slide. So these are some results for the mineral quartz. On the left are computed thermal gradients for the mineral quartz as a function of particle size. Note that the vertical axis is 0 to 2,000 micrometers, so we're talking 2 millimeters here. And the thing to notice is that the thermal gradients can be as large as 100 degrees over a millimeter. And the results for remote sensing are shown at right. These are emission spectra for the mineral quartz. The top includes the thermal gradient. The bottom does not include a thermal gradient. And what you see is the location of and appearance of spectral features change, and this has an impact on interpretation in terms of composition. Next slide, please. This is a similar calculation for the rock basalt. What you can see is the look of the thermal gradients as a function of particle size is qualitatively the same. However, the size of the gradient is not as big for basalt. This is particulate basalt as opposed to particulate quartz, and the reason is the couple of slides back when I was showing the comparison of visible and infrared length scales for absorption of radiation.
Right, you've got about 3 minutes.
Okay, next slide, please. So in conclusion, we modeled the heat transfer by conduction and radiation in the top few millimeters of the lunar surface. A large thermal gradients form up to 100 degrees in the top millimeter. The magnitude is affected by both the material and the grain size, which includes a trade-off between solar heating and infrared cooling. And for our original application, thermal gradients affect compositional interpretation from remote spectroscopic measurements. Again, we are discussing these today just to talk about their presence and see what other applications or problems they might create for science that's planned on the lunar surface. And that's it. Thank you. There are some some questions coming up in the chat. Is it okay for me to answer those?
Go right ahead.
So one of the chat questions, and let me see if I can open the chat here.
Yeah. It says, what part does...
Yeah, compaction. So good question. So the answer to that is as compaction increases, the size or the magnitude of thermal conductivity increases. And so what that does is as the conductivity increases, the size of the gradient decreases.
Okay, the next question is, if excavation exposes frozen material, it will be closer to earth heating flux.
Let's see, I'm not sure I understand the question. Are you asking if it's closer to a terrestrial subsurface temperature gradient?
Heck,
Yeah, that's a good question, and yeah, I don't. I'll have to think about that. I don't know the answer yet.
okay.